overview of fatty acid oxidation, which is also called beta oxidation. And basically, it's just breaking up the fatty acids into 2 carbon subunits of acetyl-CoA. And those can be used in the TCA cycle, and it also releases FADH2 and NADH to make ATP in the process. There's 3 overall steps, which are activation, transportation, and then the actual beta oxidation. And then the main reason for fatty acid oxidation is just to convert fat into energy.
For the activation step, this all takes place in the cytosol because in order to get into the mitochondria, the fatty acid has to be converted into an acylcarnitine. So in this first step, ATP and the fatty acid react with fatty acyl-CoA synthase to produce fatty acyladenylate, which is the main intermediate, and a pyrophosphate. The pyrophosphate then undergoes hydrolysis and becomes 2 inorganic pyrophosphate. This reaction is hydrolysis, and this hydrolysis drives the rest of the step. The fatty acyladenylate then reacts with fatty acyl-CoA synthase, releasing 1 AMP. This produces fatty acyl-CoA, and the fatty acyl-CoA can go on to the transportation step.
Now we're going to move on to the transportation step, which is where we move the molecule from the cytosol into the mitochondria. The fatty acyl-CoA is going to react with carnitine and the enzyme carnitine acyltransferase Cat1 here to produce acylcarnitine and also releasing coenzyme A. Cat1 is regulated by malonyl-CoA, which inhibits fatty acid from reacting with Cat1, thereby preventing them from entering the mitochondria. That makes this Cat1 the rate-limiting step. The enzyme acylcarnitine translocase spans the membrane, and acylcarnitine can be transported into the mitochondria while carnitine is simultaneously transported out, which conserves carnitine in this cycle. Once inside the mitochondria, this process can easily be reversed by the reaction of acylcarnitine with coenzyme A to form carnitine and fatty acyl-CoA, and then the carnitine can be transported back across the translocase with Cat2, sorry. And we also should note that acylcarnitine and carnitine are the only 2 molecules that are allowed to cross the membrane through the translocase. Now that we formed our acyl-CoA, it's ready for beta oxidation. Now that we've mentioned carnitine, we'd like to mention one disease associated with this molecule, and that is carnitine uptake deficiency, which affects newborns, specifically premature. It affects 1 in 100,000 babies, and it inhibits their ability to use carnitine correctly to convert fat into energy. It can lead to renal leakage and ultimately the inhibition of gluconeogenesis. It's very serious, and it's recommended that all newborns are tested for this disease.
Now that we have finally entered into the mitochondria, we are ready to begin beta oxidation. Beta oxidation consists of 4 overall steps: oxidation, hydration, oxidation, and cleavage. In the first step, the acyl-CoA, which in this case example it is palmitoyl-CoA, reacts with the enzyme acyl-CoA dehydrogenase and the cofactor FAD to produce trans-3-enoyl-CoA. A comment about acyl-CoA dehydrogenase: it has 3 isozymes that are specific for different length fatty acids: long, medium, and short.
And then moving on to the second step of hydration, the trans-3-enoyl-CoA is going to react with water and the enzyme enoyl-CoA hydratase to form an L-beta-hydroxyacyl-CoA.
Okay. And then the L-beta-hydroxyacyl-CoA undergoes oxidation with the enzyme hydroxyacyl-CoA dehydrogenase and the cofactor NAD to produce beta-ketoacyl-CoA.
Now on to the last step, which is cleavage. The enzyme ketoacyl-CoA thiolase, right here, which is also referred to as just KT, with coenzyme A, cleaves the thiol group from the ketoacyl-CoA, producing a fatty acyl-CoA with 2 less carbons than we started with, and an acetyl-CoA. The acetyl-CoA can enter the TCA cycle now, while the acyl-CoA can then be used to synthesize triglycerides or phospholipids. And the high levels of acetyl-CoA can inhibit the thiolase enzyme.
And then FADH2 and NADH produced from our two oxidation steps can then go on and enter the electron transport chain. FADH2 yields 2 ATP and NADH yields 3 ATP, thereby allowing your body to gain more energy. Here is an overall review of the regulatory steps. The main rate-limiting step is the transfer into the mitochondria. Malonyl-CoA, which is an intermediate, can inhibit the mitochondrial transfer of acetylcarnitine into the mitochondria, and this happens at Cat1. Another regulatory step is later on during the actual beta oxidation phase. Acetyl-CoA inhibits the enzyme thiolase, and again in the actual beta oxidation phase, high ratios of NADH to NAD+ inhibits hydroxyacyl dehydrogenase.
Now we're going to talk about odd-chain fatty acid metabolism, and this is really only important for ruminants, neonates, and adult humans under certain conditions. The three overall steps are carboxylation, epimerization, and mutation.
Okay, so we start with propionyl-CoA, and it undergoes carboxylation with the enzyme propionyl-CoA carboxylase in the cofactor biotin, as well as bicarbonate and ATP. It releases ADP and an inorganic pyrophosphate. It produces D-methylmalonyl-CoA. The D-methylmalonyl-CoA then undergoes epimerization with the enzyme methylmalonyl-CoA epimerase. The product from that reaction is L-methylmalonyl-CoA. The L-methylmalonyl-CoA then undergoes a mutation to produce succinyl-CoA. The enzyme involved is methylmalonyl-CoA mutase, and the coenzyme is B12.
And then we'd also like to mention, we're not going to go into a lot of detail about the mechanism of the mutase reaction, but do know that it's important because it requires cobalt, and that the hydrogens are not lost, they just switch places in that reaction. Alright, so now we're going to briefly cover unsaturated fatty acid oxidation. In this case, we're going to start with linoleoyl-CoA, which has a cis double bond at carbon 9 and a cis double bond at carbon 12. That molecule is going to undergo 3 cycles of beta oxidation right here, and then that's going to release 3 acetyl-CoAs, which have 6 carbons total, leaving us with this 12 carbon cis double bond at carbon 3 and carbon 6 molecule.
Okay, and so this now 12 carbon molecule reacts with anoyl-CoA isomerase. This moves this first double bond, and it makes it from a cis double bond to a trans double bond, and it moves it to carbon 2. And now it can go one round of beta oxidation right here. This releases acetyl-CoA and leaves us with a 10 carbon molecule.
Okay, and then from here, we've got the trans double bond on carbon 2 and a cis double bond on carbon 4. That's going to react with dianoyl-CoA reductase and NADPH and releases NADPH+, leaving us with this 10 carbon molecule with only the trans double bond on carbon 3.
This 10 carbon molecule with a single trans double bond at carbon 3 again reacts with the enoyl-CoA isomerase. This moves the trans double bond from carbon 3 to carbon 2. This allows the molecule to undergo 4 straight cycles of beta oxidation, and overall it releases 5 acetyl-CoA.
And one more thing that's important to remember is that unsaturated fatty acid oxidation can only happen with the enzymes anoyl-CoA isomerase and dianoyl-CoA reductase.